Um, yeah, so the meeting is being recorded. You all can send it to that. So we'll upload that to our YouTube at some point if anyone who missed this wants to watch it. And, like a lot of you know, we're a new society. So this is our first event. I want to thank you all very much for coming. The whole team's put a lot of work into this, especially Emma, who's essentially made the whole PowerPoint herself, and is going to give a talk about AI. So we hope you enjoy the event. We hope you learn a lot about AI itself, and then hopefully you come to our future events as well. We're going to have teaching, socials, and some more seminars run throughout the year. And just throughout the talk, if you have any questions, just put them in the chat. Emma's going to have some time at the end to kind of answer any questions you might have. So yeah, just put them in the chat if you have any. So thank you all very much for coming, and I'm going to pass over to Emma now.
Hi, I'll just share my screen. Okay, hopefully you can all see that. Okay, so hello everyone, and thank you for joining. My name's Emma, and I'm an MBPhD student, which basically means a medical student who's taken some time out to do a PhD. I did my PhD with the computational biology group in the computer science department, and I focused on predicting patient outcomes in various intensive care units. So things like predicting mortality, length of stay in hospital, and readmission risk. And I used various deep learning techniques to do that, which is a type of AI. And I'm a fifth-year medic now. I'm also one of the teaching leads for the brand new Society for AI in Medicine, and I'm very excited to be giving the first ever talk. Okay, so what do we aim to achieve with our society? Well, AI for medicine is by definition an interdisciplinary area, which means that we need expertise from technical domains as well as clinical. And in fact, we need people from ethics and law backgrounds and other domains as well. I'm going to assume that this audience is a bit of a mix, so I'm not going to make any assumptions about background knowledge. For healthcare students, our society aims to fill in some of the gaps that we feel are present in the medical curriculum. And given the direction that we're moving in the near future, it will become important that the next generation of doctors and vets are proficient with using this kind of technology. And by that, we mean to critically assess the appropriateness of an AI solution, knowing the strengths and weaknesses, and being able to understand the literature, at least on an overview level. And for some, being able to collaborate with research groups and co-design solutions to healthcare problems. There are far too many projects which focus on solving problems that have no or very limited clinical impact. And that's because too many people currently building the solutions don't understand the clinical context that they're designing them for. So with that in mind, for students from other subject areas, we'd like to give you the tools to be able to assess the clinical impact of a potential application. And obviously that would involve speaking to clinicians, but I think it's helpful to have a basic understanding of the common requirements and challenges of a healthcare application so that you can ask the right questions. So I thought we'd start with finding out what AI means to the audience that we have here. So I'll give you a couple of minutes to fill in this poll, and I'll also just paste the link in the chat. So if you could fill in on that link, I'll give you a couple of minutes. Cool. We're seeing robots, computers, data. Yep. Complex machine learning, algorithms. Cool. All right. I'm going to stop it there. And switch back. Okay, so do let me know if you can't see it, by the way. It seems like we already have a pretty good idea of what artificial intelligence means. The dictionary definition is actually the theory and development of computer systems that are able to perform tasks normally requiring human intelligence, such as visual perception, speech recognition, decision-making, and translation between languages. So essentially, it means replacing a task that would normally require a human to do it. And it can include software, hardware, or both. And note that the definition of AI is dynamic. So easier tasks that might have previously been considered AI are no longer considered AI. So one example would be early character recognition systems. And a lot of these things are still the subject of debate. So now that we've defined AI, let's talk about machine learning, which is one way of applying AI. It uses statistics to allow machines to improve with experience. And by that, we mean trial and error with data. Yeah, so if we imagine that we have an AI agent that's learning to estimate the likelihood of death in a patient, it's given the patient data and then it guesses whether or not the patient survived or died. And then if it gets it wrong, then the model is told to update itself so that it's more likely to predict the correct answer in future. Deep learning is a particular type of machine learning that uses neural networks specifically to do the learning from experience. And note that in the terms deep learning and neural networks are interchangeable, so they mean the same thing. And it's becoming more and more popular because it can be easier to deploy than the older machine learning methods. And this is because in traditional ML, you'd have to spend a lot of time preparing the data, whereas one of the appeals of deep learning is that it can handle data in a much more raw format. So now that we mentioned traditional ML, I just wanted to show you that it includes quite a few methods. So the ones listed here are certainly not an exhaustive list. Quite a few of them are being used less now because neural networks are very powerful if you've got the data to learn from. But sometimes there are important reasons why you might not want to use deep learning, like if you need to take a mechanistic approach because you already know a lot about the problem that you're modeling, or you might want a method that's transparent and easy to interpret. You might only have a small amount of data, or you might want to explicitly represent uncertainty or insert a prior probability or expectation into the model. Okay, so I'm going to talk a little bit about deep learning now because it's just very common and a very wide selection of AI applications use it in some form, and it's become the most rapidly expanding area of machine learning. So the inspiration for deep learning comes from neuroscience. We know that in the brain we have networks of neurons which connect up to propagate signals in layers. And with each successive layer, there's typically a higher level of processing. So a single neuron, for example, the one in green here, will aggregate all of the signals coming in from other neurons, and then it will perform a computation to decide whether or not to fire based on if the signal coming in exceeds a certain level of threshold. And if it does exceed that threshold, then it will propagate the signal further down the network. And we have reason to believe that this structure of neurons could be really useful, because the brain can apply itself to a very wide range of problems. And in fact, if something happens like a stroke or a limb amputation, the brain can sometimes remodel itself to restore or replace the function of the damaged brain region. So the structure of neurons in the brain is really flexible. So discoveries from neuroscience laid the foundations for deep learning, but we make a few tweaks in the computerized version. So for example, the decision on whether or not to fire an artificial neuron is no longer binary, like in the brain, but instead it's a graded activation signal, and that can be either positive or negative, as can be seen by the lines shown in red. We also ignore any timing elements, so all of the inputs are just synchronized by default. And we use an algorithm called backpropagation to learn the weightings associated with each artificial neuron using the feedback from data. And this is kind of similar to how learning happens in the brain, because in the brain, you just modify the strength of the synapses between neurons. It's just that in deep learning, we use a different optimization algorithm. So deep learning is suited to learning from huge data sets, so big that a human couldn't possibly have time to look at sometimes. And humans are really good at figuring out causal relationships quickly. But what they're less good at doing is teasing out subtle correlations. So things that work well for very rare subsets of patients in unique circumstances. And that's because you can't store data from hundreds of thousands of patients in your memory. But deep learning can go way beyond the limits of how many patients that a doctor could possibly see in a lifetime. And this leads on to the next point, which is that deep learning can scale very easily. So the main upfront cost is the designing of the algorithm. But if you have a big data set, then it can be cheap and easy to feed in lots of data. And if you keep the algorithm up to date over time, then you can just simply feed in the latest batch of data. It's also very good at specializing, and it can exploit reliable patterns in the data without getting tired or bored like humans might. And it can update itself in real time as well. So for example, if you have a patient in the hospital and you want to predict their chance of surviving life-threatening sepsis, every time you take a measurement of the patient, you can then ask the model for an updated assessment. And this isn't really feasible at the moment with the busy consultants on the ward. So that's a definitive advantage. And finally, it's good when you have a complicated task where very small improvements can make a really big impact. So one example would be screening. So we have hundreds of thousands of women every year that need screening for breast cancer. And most of them will be fine, but a few of them will have cancers. And some of these are really easy to spot, but others can be really subtle on the imaging. And past a certain point, it can be very difficult to treat cancer. And it becomes a question of when and not if the patient's going to die. But if we spot the cancer really early, then the patient has a much better chance of survival. And this is an area where AI could make a big impact, because you could increase the capacity of screening by easing the workload demands from highly trained specialists. And you could potentially identify problems even earlier, which would translate to real differences in outcome. So now let's talk about the negatives. So AI systems have no sense of intrinsic morality. So you have to tell it explicitly how to behave in certain scenarios. So for example, with a self-driving car, you would need to tell it explicitly not to hit other pedestrians on the way to get to a destination, even if by hitting the pedestrian, it's the most efficient route to the destination. The tricky thing is that you can't always predict the behavior of other cars and pedestrians. So the developers of the self-driving cars need to consider the possible ethical scenarios, like what if you could choose between hitting a pedestrian or another car? What if that's a lamppost or a pedestrian? Should you prioritize the safety of the people inside the car, or is it acceptable to risk the people inside the car to avoid killing someone else? And these decisions really matter. And when it comes to healthcare, these kind of ethical dilemmas are even more frequent. You know, you need to decide who gets an organ, or whether this person's life is worth spending our limited NHS resources on. And on top of that, we've got difficult questions like, if an AI makes a decision, whose fault are the consequences? Is it the authorizing clinician? Is it the AI algorithm? Is it the developers? Is it the NHS trust that bought the algorithm? Is it the patient? Or is it nobody's fault? Next, we have highly deterministic problems. So because deep learning is stochastic, when you train a neural network, the final performance will usually be slightly different with each iteration of training. And this is because it's sensitive to things like the order in which you present the data, or the initial values assigned to the weights of the network. So this means that it's usually impossible to get solid guarantees for the performance of the algorithm. And in cases where the problem that you're modeling is heavily deterministic, like if it relies heavily on basic laws of physics, then you could quite easily get predictions from the deep learning that completely violate these rules. And when you have a very good understanding of the problem, then it can sometimes be worth just simulating the system rather than trying to predict the outcome in question using deep learning. Data is a very obvious limitation. So if you don't give the model good data, then it'll give you meaningless results. Deep learning is especially data hungry because it doesn't make any assumptions about the structure of the data up front. And so this means that it takes a lot of examples just to get a feel for the task before it can really refine the predictions. Whereas humans don't start from the ground up. You know, they already understand physics. They've been to medical school, they understand the theory. So, you know, they already know to look at certain parts of the X-ray or whatever. You know, the deep learning doesn't have that advantage. Generalizability is a terrible problem in machine learning. If you try to apply a model that was trained on one set of data to a similar situation, it can fail miserably. And, you know, catastrophic medical errors really aren't ideal. The difference doesn't even have to be very big. It could be a different hospital, or it could be just a subtly different task, like predicting length of hospital stay instead of mortality. So you always need to check that the training data is very representative of the task that you, or the setting that you want to apply it to. Interpretability is another classic problem. We're often given close to no information about why the algorithms come to a certain decision. How can we trust that the algorithm knows what it's doing in every scenario? And even if you can trust it, can it even be useful if the doctor doesn't understand why it's come to the decision, or they don't agree with the decision? Ideally, we'd like the doctor to work together with the algorithm to make the best decision for the patient. But this loops back to the ethical point. You know, is it better for the doctor to blindly trust an AI that tends to be more accurate than they are, or should they go with the decision that they can actually defend the rationale behind? These are difficult questions. And related to the above point about the rationale behind decisions, machine learning methods typically look for correlations in historical data. And this makes it nearby impossible to discern a causal relationship because you can't interact with the real world. So you can't separate correlation from causation. Clinical trials get around that because you can actively intervene in the real world, but with AI, we'd be getting into messy territory, allowing AI agents to experiment on patients or whatever to tease out causal relationships. And finally, we have tasks where the outcome can't be clearly defined. So we mentioned that one of the strengths of deep learning is the ability to learn automatically and semi-independently from humans. And if the task is something like do the surgery, then it can be really difficult to decide whether the agents perform correctly. So we can do things like imitation learning, where you say, copy this movement, and that's relatively easy to compare any differences in the movement between the clinician and the robot. But actually every patient's different, so the learning should ideally be adaptive to the patient's specific anatomy. And for tasks where it's really difficult to define whether the AI has done something correctly or not, we're forced to have a human in the loop to say either, yes, that was good, or no, you need to practice that part of the surgery. And this really slows down the learning process because you're now dependent on a human. And so there's now a more reasonable limit on the amount of data that you can see and stuff like that. So once again, we go back to ethics because also getting robots to learn and practice surgery is another ethical nightmare. Okay. So with that background in deep learning, let's dive into a practical example. So let's say that our task is to predict how long a patient's going to stay in hospital. And actually, this was one of the major tasks of my PhD. Possible input data could include the patient's age, their sex, what their diagnosis is. The list goes on, but we'll keep it simple with only 3 things here. An easy method to use is linear regression, which hopefully will be familiar to a lot of you. If you don't know it by linear regression, you might recognize the term line of best fit or y = mx + c from school. In our case, we don't just have one independent variable, we've got multiple. We've got the age, sex, etc. We multiply each aspect by its own coefficient. And then we add an intercept, which is basically the default length of stay if all the features are 0. And if we add up the results, then we should get a prediction. And this is quite a simple model because it assumes a linear relationship between the variables and the outcome. So linear relationships are just basically straight lines between the outcome y and the input variable x. So in this case, y could be the length of stay and x could be the age. So the older the patient, the longer the length of stay. One of the limitations of linear regression is that actually a lot of problems aren't linear, but we'll park that point for now. We can actually represent this linear regression problem as a simple neural network. So in the input layer, we've got what we call a node for each variable, which is shown as these blue circles here. The scaling factors are called weights. So they're represented by W1 to W3. And these indicate how strong the connection is between the variable and the output. If the weight is higher, then it means that the output is more dependent on that variable compared to the others. And we can simplify the notation to just say y = wx + b, where x contains all of the variables in the input and w will contain as many weights as variables. And we call w the parameters of the network. And these are the things that we need to learn during the training process to run the model. So what if we've got 2 layers? The answer is pretty much more of the same. So now we've got an intermediate layer in the network labeled H for hidden layer. And we've got a set of weights representing each link from the first layer to the hidden layer, so 9 in total over here, represented by W1. And you've got a second set of weights for the second layer, W2, so 3 in total. And we apply each layer in turn to obtain the output as before. As we add more layers to the network, we can represent more and more complex functions, but we've got more weights that we need to learn, so the training is going to get slower as the learning gets deeper. I'll just mention that part of the power of stacking multiple layers together is that you can add a non-linear function between the layers, which means that you can start to represent very complicated, highly non-linear functions, which increases the capacity of the model. The networks that I've shown here are actually called fully connected neural networks because every blue circle or node has a connection to every other node in the layer before and after it. But a lot of the art of deep learning is to modify the connectivity of these neurons so that the model is particularly good at learning to do certain tasks. And you can use prior knowledge about the data or the task in order to do that. So I've put this slide in particularly with the medics and vets in mind. So the first picture is of a convolutional neural network, which is a specialized network for processing images. It's no longer fully connected, but instead you've got small sections of the image which are processed locally to look for features of interest. So this is a bit like in the visual cortex of the brain where you've got specialized connectivity to form simple cells in V1, which have receptive fields that respond to lines and edges in an image. So this is useful because if you can learn to recognize edges in an image, then you can find the outlines of objects. So you can pretty much throw away 99% of the information in an image, and it's still easy to classify. In fact, it might even be even easier because you don't have distracting information. And note that this kind of approach wouldn't help you to distinguish computer-generated images of random noise. It's specifically an adaptation to take advantage of our environment. And we can copy this idea with neural networks as well, shown in the top image. And we can also make networks to be particularly good at processing other kinds of medical data. And actually that was a heavy focus of my PhD. So with that, I'm going to move on to show you some cool examples of AI in medicine. So first of all, we've got medical computer vision, which is currently the most extensive subfield of AI in medicine. In about 2012, there was a big explosion in deep learning for computer vision, and it has the potential to be used in radiology, pathology, dermatology, ophthalmology, cardiology, and surgery. And to be honest, like pretty much every area of medicine is going to have some dependency on imaging of some form, or videos as well. So to give you a couple of examples, this study in 2018 used an improved version of a UNet, which is a type of convolutional neural network, to automatically detect the position of surgical instruments in videos taken by the Da Vinci system, which is a surgical robot currently operated exclusively by humans, but identifying instruments and distinguishing them from biological tissues would be a prerequisite for AI-assisted surgeries. And an example from histopathology, a study by Rana et al. Last year used a different type of network called a GAN to artificially apply a H&E stain to unstained tissue biopsies. So the top row is the original biopsy, and the second row is the genuine stain, and the third row is the computational stain. So doctors couldn't tell the difference between these two, and there was no difference in the ability of the pathologist to annotate the images either. Then we move on to natural language processing, which is now very powerful. As electronic health records move increasingly to, basically any health records become increasingly electronic, we've now got a huge bank of relatively unstructured text in patient records, which can be analysed. And on top of that, we've got millions of research articles about all sorts of medical conditions, which can also be analysed. It might be much, much easier to do a review article in the future. And kind of worryingly, it might also be possible to get the AI to generate an entire research paper for you, including the figures. But I won't get onto that. In terms of patient-facing solutions, medical chatbots can be used to triage people, to track symptoms, even provide some kind of therapy for patients with mental health problems, for example. Some studies like this one's on students, actually found it to work, not as well as cognitive behavioral therapy with an actual human, but they still found some promise in the approach. And voice analysis also comes under natural language processing. And this study found some promising results to suggest that we might be able to stage dementia just from voice analysis alone. I'm shamelessly including my own work here to demonstrate how AI could be used for time varying data like heart rates and blood pressures, etc., in intensive care units. So we showed that it's possible to predict length of stay much more accurately than doctors. And this is useful because it allows hospitals to plan ahead for the expected bed capacity in intensive care units, which at the moment is especially topical with the need to plan around COVID-19. On the graph on the left, I'm showing that you can give this model a set of 16 patients currently in the unit, along with their specific data. And you can ask them how many of them will still be there tomorrow or in 2 or 3 days, etc. And knowing that information could enable more sophisticated scheduling of risky elective surgeries, or help to identify patients that are almost ready to be discharged, or on the flip side, warn against discharging patients too early. And this kind of technology will help to optimize the available capacity in the intensive care unit, but hopefully not overload it either. AI can be integrated with medical devices like wearables and implants. Currently, diabetes type 1 is associated with significant excess mortality and morbidity. They can expect to live about 10 years less than other people, and they're at higher risk of getting heart disease and stroke and kidney disease, and also losing their eyesight. And it's really hard to control blood sugars as well as a real pancreas can. But that might change with the introduction of these intelligent insulin pump systems that will hopefully take over the role of the real pancreas and be less intrusive to a person's life. Then there's machine learning for new drug discovery. So this can include techniques to predict which molecules from a set of candidates would be able to bind to biological targets most effectively, which is shown here on the left. It could also be methods to design brand new synthetic molecules that are tailored to a particular target. And it could also be the repurposing of existing drugs that have already been licensed for certain conditions to identify new use cases for the drug. And this has got the advantage that you don't need to go through all the stages of clinical trials again. You just need to prove that it works in the new condition. So you don't need to prove it's safe on animals and human volunteers. There's a company here in Cambridge called HealX, which actually do just that. And yeah, there are so many more applications of AI in medicine, and I couldn't possibly attempt a comprehensive overview today, but we'll be hosting more events later on in the year from other people. Finally, I'll just talk about some of the reasons why AI for medicine is going to expand over the next few years. So we have increasing healthcare expenditures, both on a per patient level and globally. And we have an imbalance between the number of clinical workers like doctors and nurses and patients. And we've now got an aging population, which is going to increase the burden of disease, especially the chronic metabolic type diseases like type 2 diabetes, stroke, heart disease, cancer. And AI will help to redress this balance by alleviating some of the workload. So especially the kind of repetitive tasks that require analyzing huge amounts of data, as I kind of alluded to earlier in the talk. On the flip side of that, we do have significant barriers to the introduction of AI. So, for example, some very difficult ethical issues, which I've already touched on a little bit. I didn't really talk about bias, which is another big problem whenever there's bias in the data set that you're training on. So, for example, Black women don't get taken as seriously when they say that they're in pain during childbirth, and they're often prescribed significantly less pain medication than white women. They're also more likely to suffer serious complications and death, even after adjusting for socioeconomic status and other factors. So we need to make sure that AI systems are fair and safe for everybody. And there's a lack of understanding among healthcare professionals, and understandably some wariness to adopt the systems. And actually, I would encourage the wariness, and I'm also very wary, but I think it's important to be wary for the right reasons. So, you know, with the knowledge of where it can enhance patient care and where we need to be careful. There are also issues around data privacy and security. Again, I haven't had time to go into this too much, but if you trained a machine learning algorithm on some patient data, sometimes that algorithm can actually store information about those patients. So if you know what you're doing, it's possible to actually uncover some confidential information about the patients just by working backwards from the learned weights in the network. There's also interoperability issues between different software systems. So this is already a problem in healthcare. For example, GPs in hospitals not being able to access each other's data. But then if you imagine adding a bunch of other technology, the problem just snowballs. And finally, we're in the process of working out how to regulate AI for medicine. So at the moment, the approval comes under the medical devices legislation, but it's not really written for purpose. So for example, if you want to make an update to the system, you need to submit a new request every time you make an update. But with AI, you might want to update the systems all the time with the latest training data. So it can become quite cumbersome. And with that, I'll end this introductory talk. I hope that you've learned something about AI. I hope that you now know what the difference between AI, machine learning, and deep learning are. Some of the strengths and limitations of the technology, some current applications in healthcare, and what factors are currently influencing the adoption of AI systems in medicine. I'll open up the floor to questions, so you can either write them in the chat or maybe even unmute. I'll maybe stop sharing for the moment.
Is it okay if I speak?
Yeah.
All right. I just want to say thank you and a very good presentation. And yeah, I already have some ideas for projects. I'm not sure I have a question yet, but this sounds very cool. So if someone had time to come up with a question, I will let them speak.
Hi, that was a great presentation. Thank you very much. I was just wondering if you had to, in terms of technical capabilities for medical students, for example, to learn, what would be the sort of, what would be a good taster activity to get started on if they were interested in doing this sort of stuff?
It's a question that I've been thinking about a lot and we'll be thinking about a lot in the society. I think we're going to hope to host some events that are going to be tailored at people that are thinking about sort of dipping their toe into some AI and getting started. I think it kind of depends like what your interest is. So are you interested in just learning more about the technologies, or are you excited to be using it in practice, or are you actually interested in getting involved? So getting involved in a project or learning how to code or something like that. I think we're planning as a society to host an event that will go through like some very, very simple bare bones models, which should involve a practical element. So if people are interested in doing that, then I'd recommend kind of signing up to the society and you know, staying up to date. There are lots of resources online as well to learn how to program. It's probably one of the easiest things to teach yourself to do. Yeah, so does that answer your question?
Yeah, thank you.
Sorry, I have a question. Thank you, Emma. That was a really good presentation, except for me, especially for me, who doesn't have like a background in AI. Just out of curiosity, I was thinking, like, is there a patent issue in terms of algorithm in AI? For example, if like two teams simultaneously developed a very similar algorithm for analyzing a particular set of images, I mean, like, how do they patent that? Like, do we have to pay if we are using someone else's algorithm?
Great question. First of all, just a disclaimer, I'm really not an expert in this side of it. I'm more just involved in the sort of research end of things. I imagine it would be very messy because you know, the pace of AI is incredible. Like, it is one of the most fast-paced areas of machine learning. So I think, you know, it's going to be incredibly challenging probably to patent things, but yeah, I don't know about kind of if two groups do the same thing at the same time, and yeah, I'm really not an expert in that.
Thank you. Anyway, it's something like I'll be interested to find out more about.
I've got a question in the chat from Erin. Why did you choose computational biology as part of your MBPhD? So I guess what I was doing is more, I guess, computational clinical informatics. Usually computational biology is like machine learning for genetics or something like that. Basically, I wasn't really sure what I wanted to do. I just knew that I was interested in maths and physics, and I quite enjoyed, you know, I guess I didn't necessarily enjoy using computers. It was more just kind of logic and solving problems and things like that. And I was just thinking about, you know, what are the areas that are emerging that are really going to impact a lot of patients. So I thought about things like, am I interested in medical robotics or something like that, because I did engineering as my third year. But in the end, I think once I'd kind of read a little bit about AI, I was thinking, wow, this is going to be a really huge part of clinical medicine in the future. And, you know, it's something that I think maybe would be really, really cool. And there's also not that many people that are at the interface between medicine and machine learning. It's quite a small group of people, really. In fact, most people working in the area are from a a technical background and they've moved into medical things, but they actually don't have that understanding of the clinical world, which is so important. It's something that I'm realizing later on, like as I was finishing my PhD, I realized actually to make an impact in this area, you have to understand the context in which the solution is going to be deployed in. I've got another question. So from a mathmo with programming experience, what opportunities will there be in the society for people like me? So it's great that we're having a mixture of people from different backgrounds. I think it would be really great for people that are interested in moving into the field to, I guess, gain an appreciation for the kind of difficulties that are specific to medical applications. So, you know, there are a few people that have the kind of expertise to build the solutions, but there are some sort of unique problems in medical type data that often people don't know about. And if you don't understand the data very well, that can lead to you making mistakes in like the training and stuff. So one example is, you know, if you didn't really understand what you're doing, you know, you could perhaps treat all admissions to a hospital as a separate data point, but then you realize, oh, actually some patients have come into the unit multiple times, and then you've now got a problem where you've got the same patient appearing in your training data, and that's also in your test set, and you know, that's a problem. When I was working with some medical data, I once, you know, just as a sanity check, looked at some of the diagnoses that were present, and I found that, like, I think it was something like 20% of patients were diagnosed with appendicitis. So I was thinking, this is kind of a lot of patients to be diagnosed with this. And it turns out that it was some sort of, the form would require a diagnosis to be put in. And so people would just click on the drop down list, and that was just the first one. So people just put that, and everyone in the hospital just knew that it meant I have no clue what's going on. I just have to put a diagnosis in. But I think just things like, you know, appreciating that these kind of problems can arise and knowing the importance of collaborating with clinicians. And I think if you understand a little bit about what the medical world is like or how doctors think, it can really help you to communicate with the clinician and work with them on the project. Hopefully that makes sense. But yeah, I think if you attend some of the future events, you know, we'll have people from medical backgrounds, you know, talking about their various projects in medical AI. So how can AI go about deriving a physical law? So yeah, so you can, so it's basically, a lot of this is about, so when you set up the problem, so yeah, when you set up the model, you can often design the model in a way such that it's going to represent certain things. So for example, you know, you can take a mechanistic approach, but then still use machine learning. So with a mechanistic approach, you can sort of say, well, I'm going to represent this this thing in the person, like the blood pressure in this way, and I'm going to represent something else like the vasopressors like this, and then you're trying to actually teach the model to give you outputs that are then interpretable to people and mean something. In terms of deriving a physical law, maybe I don't quite, maybe that's a very high level. If you're talking about kind of, you know, being able to discover like a new theory about something, I think AI is quite far away from being that intelligent, because, you know, that's a very high level that we're talking there of abstract reasoning. But yeah, they're definitely, you know, you can be quite specific in the way that you set up the problem to get certain insights that you're wanting.
All right, if there's no more questions, just put one in if you have any. Emma, do you have anything else to say?
No, not really, apart from just yeah, thank you for coming to the first ever talk, and yeah, hopefully this is the start of developing a little community that is very excited about AI in medicine. I'm very passionate about it, and yeah, please come to the future events.
Yep, I want to say the same thing. Oh wait, was that someone question?
Yeah, just one more thing. Maybe there already exists something like this, but it would be fun to have a Facebook group and or a WhatsApp group or something like that, because this is something I would really like to talk to other people about. And yeah, I see some names here, but if you could make that for us.
Okay. Yeah, we'll consider making a Facebook group so you can kind of text on it. Someone also mentioned Discord, but I imagine that's less popular, so having Messenger is the best way. We might implement that in the next few weeks. Thank you for the idea. So yeah, we'll think about that. Yeah, once again, thank you very much for coming to our first event. As it is our first event, we're not sure what we've done, the best and what we could have done better. So we kind of sent out a feedback form. I've emailed it out to everyone that attended today, and Afra has put the feedback form in the chat as well. If you could fill that in, it would be really helpful. We can know what we can do better next time. It is only our first event, but hopefully you really enjoyed it. I think it was really good. Emma put a lot of effort into that, and you can tell because it flowed very nicely, and we all learned a lot. We'd also like to thank the rest of the team as well for helping kind of publicize it, getting the event set up, and similar things like that. So yeah, once again, thank you all very much for coming. If you have any questions for the society, you can always message the Facebook group or email the email that's attached on the bottom of the emails. So yeah, if anyone has any more questions, you can ask now. Otherwise, thank you very much for coming.